SpaceX's first version 3 booster just failed during gas systems testing, and this represents a critical inflection point for Starship's operational timeline. Booster 18's failure reveals systemic challenges with the next-generation hardware that directly impacts Flight 12 and the V3 transition schedule. Critical development from Starbase. SpaceX's Booster 18, the company's first complete version 3 Super Heavy prototype, experienced a catastrophic gas systems failure during ground testing operations. The data confirms this isn't just another routine development setback. This represents a decisive inflection point for Starship's entire operational timeline. Here's the smoking gun. Booster 18 was designed to validate the most significant hardware leap in Starship's development history. Internal analysis shows version 3 represents a complete generational shift, engineered to support 33 Raptor 3 engines, producing a combined 7,590 metric tons of sea-level thrust. That's a 40% increase over current version 2 configurations operating at 5,400 metric tons. Reports reveal the gas system's failure occurred during pressure regulation testing, a critical subsystem that manages propellant flow to those 33 Raptor 3 engines. Industry sources indicate this failure pattern differs significantly from previous version 1 and version 2 development cycles, where most early failures involved engine-specific issues rather than fundamental pressure management architecture. The strategic implications are immediate. SpaceX now faces a decisive choice for Flight 12. Program data suggests 3 options: revert to proven version 2 hardware, delay operations to address version 3 systemic issues, or attempt a hybrid configuration. Each path carries documented timeline and budget consequences. According to internal manufacturing schedules, version 3 hardware was positioned as the foundation for SpaceX's 2025 operational scaling. The system was specifically designed to handle Raptor 3's increased chamber pressure, operating at 300 bar compared to Raptor 2's 270 bar. That 11% pressure increase demands precision in gas systems management. Here's where the analysis gets critical. This isn't an isolated hardware test. Booster 18's failure validates or invalidates an entire production philosophy. SpaceX has 4 additional version 3 boosters in various completion stages. Boosters 19 through 22, representing approximately $360 million in committed hardware development. The data reveals a fundamental question about version 3's readiness timeline. Previous generational transitions, from Falcon 1 to Falcon 9, from Raptor 1 to Raptor 2, typically required 12 to 18 months of iterative development following first major system failures. If version 3 follows historical precedent, this single gas systems failure could extend full operational capability to Q4 2025. Operational pressure adds another layer of strategic complexity. Version 3 wasn't developed for incremental improvement. It was engineered to support SpaceX's accelerated Starlink deployment schedule and NASA's Artemis timeline requirements. The 40% thrust increase directly enables heavier payload configurations critical for both commercial and government contracts. The data reveals a pattern that fundamentally changes how we should evaluate this failure. When SpaceX transitioned from Falcon 1 to Falcon 9 in 2008, their first next-generation booster experienced similar gas system anomalies during ground testing. That failure extended their development timeline by 18 months, a precedent that makes version 3's current situation critically significant. Industry sources confirm that gas systems failures typically indicate pressure regulation architecture issues. And here's where the technical analysis gets concerning. Raptor 3 engines operate at significantly higher chamber pressures than their predecessors, requiring entirely redesigned pressure management systems throughout the vehicle. Internal program data suggests Booster 18's failure occurred specifically within these upgraded pressure regulation circuits. The strategic timeline pressure adds another decisive factor. SpaceX engineered version 3 operations to begin by Q2 2025, not for arbitrary milestones, but to support a documented 40% increase in Starlink deployment rates. Industry analysts note this timeline directly correlates with SpaceX's satellite constellation completion schedule, which generates approximately $6.6 billion annually in projected revenue. Budget implications reveal the systemic scope of this challenge. Each Starship booster represents approximately $90 million in hardware costs, but the downstream manufacturing implications are more significant. Program documents show SpaceX has invested over $400 million in version 3 tooling and production line modifications. A fundamental design revision would require reconfiguring these manufacturing systems, extending costs well beyond the immediate hardware loss. Competitive analysis reveals why this timing creates strategic pressure. China's Long March 9 development timeline shows first launch capability by 2027, with payload specifications indicating 140 metric tons to low Earth orbit. That's 40% of Starship's target capability, but represents direct competitive pressure on SpaceX's commercial launch dominance. Any version 3 delay reduces SpaceX's operational advantage window. The manufacturing data confirms this failure affects far more than a single booster. Reports indicate SpaceX has 4 additional version 3 boosters in various completion stages. Boosters 19, 20, 21, and 22. All incorporate the same pressure regulation architecture that failed during Booster 18's testing. If the failure represents a systemic design issue rather than manufacturing variance, the entire version 3 batch requires hardware modifications. Here's the critical factor that changes everything. SpaceX's manufacturing efficiency depends on flight validation data to optimize production processes. Version 2 boosters achieved this optimization after 6 successful flights, reducing manufacturing time from 8 months to 4 months per vehicle. Version 3's failure resets this learning curve, potentially extending manufacturing timelines just as demand for launch services reaches peak levels. Industry analysts note an unprecedented operational complexity. Version 3 wasn't designed for incremental improvement. It represents a complete architecture redesign supporting 33 Raptor 3 engines versus version 2's 33 Raptor 2 engines. The thrust increase from 7,590 metric tons to 10,600 metric tons requires fundamental changes to vehicle structure, propellant management, and flight control systems. A single-point failure in gas systems suggests broader integration challenges across all these interconnected systems. Critical development. SpaceX now faces a decisive 3-option matrix that will define Starship's operational trajectory through 2025. Internal analysis shows the decision tree branches into revert to version 2 hardware for Flight 12, maintaining current timeline. Delay operations for version 3 fixes, extending development by 4 to 6 months. Or implement a hybrid configuration using version 2 booster with version 3 ship, each option carrying distinct strategic implications. The data confirms that any version 3 delay beyond Q2 2025 creates cascading timeline pressure across multiple programs. NASA's Artemis timeline analysis reveals Starship HLS depends on operational version 3 capability by late 2025. Pushing this milestone to Q4 2025 compresses lunar mission preparation windows to just 18 months. Industry sources indicate NASA program managers are conducting weekly reviews of SpaceX's version 3 development status, with particular focus on gas systems reliability metrics. Here's where the competitive implications become decisive. Blue Origin's New Glenn faces its own operational timeline pressures. But any 6+ month Starship delay provides critical development runway. Reports confirm that ULA and Blue Origin are positioning for potential NASA contract modifications if Starship version 3 encounters extended delays. The strategic calculus is straightforward. Operational capability gaps create market opportunities. Manufacturing data reveals version 3 production line optimization requires successful flight validation to finalize tooling and quality control processes. Each additional ground failure extends the learning curve by approximately 8 to 12 weeks as engineering teams implement systematic fixes across the production pipeline. Cost analysis shows this manufacturing delay pattern could add $200 to $300 million to overall program development costs.